Alright, are we ready, guys? Let's look at the answer now, yeah? Okay, first question. Summer, are you ready?
Yeah, I'm ready.
Good. Question 1, what is EMF?
Battery, we imagine it as a battery and internal resistance inside of the battery, and the volt of the EMF is the volt of the internal resistor.
Close enough. The volt of the internal resistor?
Yes.
Voltage.
Oh, it's okay. That'll do. Yeah. I think in the exam, you don't have to write as much as that.
Just to write the last sentence.
You could just write in the exam, the EMF is the voltage provided by a battery. Normally with internal resistance. Okay. Part 2.
R equals.
VIR. They want the resistance now, is it?
Yeah.
Yes.
So we have all the information we need? Or is V over I? Do we know V?
14.5.
14.5. Yeah.
I have a question.
Yeah.
Stephen.
Yeah.
If I add the 15 with 14.5.
Add?
Yes.
Add?
Because it
No.
is
No.
yeah.
No, minus.
I know that.
Yeah.
Yes.
Yeah.
So the EMF is a minus voltage.
No, the EMF is plus
Yes.
and the lamp is minus.
So just the whole voltage is 0.5.
No, we'll get to it. We'll look at it. Don't worry.
Yeah.
Now, Summer, the next part is the internal resistance. Okay, so what you have is this. You have
EF minus rho over.
yeah. That's it. Yeah. Oh. So this is OR.
Yes.
This is 15.
Yes. And the other.
This here is
14.5.
14.5. Correct. Yeah. And we also know that it's 58 ohms, and we want this one. So you can say 15 minus 14.5 minus, oh, what's the current as well? 0.25.
Yes.
Minus I or equals 0. Whose rule am I using?
So plus.
Kirchhoff's
Yeah.
loop rule.
Yes.
So the OR will be 0.5 over 0.25. 2 ohms.
But in the first questions,
Yeah.
how to determine that if we don't need to use in parallel the voltage is plus.
Ah. In parallel,
Yeah.
the voltage is the same.
Let's see.
You mean in series?
Oh, in series.
Yeah. You're right, they do add.
Yes.
But that's... Oh, okay, alright, fine. So, look, yeah, okay, so look, these two
Yeah.
Voltages, the voltage here, if I call it V1,
Yes.
and the voltage here, I'll call it V2.
Yes.
You're right, V1 plus V2 should equal 15.
Yes.
Yeah. Yeah. So, you get V1 equals 0.5. Yeah. So you know the V1 here. So you can say OR is V over I, which is 0.5 over 0.25.
So we
Same answer.
also can like two resistor.
Yeah. Yeah. Yeah.
Okay.
Okay. Right. Switch A is closed, and now the current is 2.
Yes.
So let me draw this.
Let's
Yeah, well, first I just want to draw what we have.
We don't
What-
need to draw.
Let me draw it. Let me, please. I like to, okay? It helps me. I'm not as smart as you guys, okay?
No.
14.5. Right, what's this? This is still 2 ohms. Okay? And then it splits here to the motor and to the lamp. And the lamp is still 58 ohms. And the current is 2 amps. Okay? And the question is, what happens to the brightness here? Yeah?
Yes.
So, and then it says, explain why the brightness changes.
Yes.
So I want to do both together. Okay, so let's see. Do we know how big the motor is?
No.
We don't know the resistance in the motor?
No. So.
We don't know anything about the motor.
Yes.
Okay, so we'll just call it X.
Yes.
So we know...
You lost the switch.
That's not important.
You said you like.
Okay, I know, I say many things. Yeah, okay, there's the switch now. Alright, it's closed. Okay, so what was I saying? What? It is closed.
See, you can see the graph.
Yeah, but now it's closed.
No.
Huh?
It's not similar.
It's similar enough.
No, you can see the
What?
graph. See where is the switch?
So what?
Oh, it's different.
I
Actually,
know.
It's different.
No, I do, I know. Okay, I know. Can I continue? Right, okay, you're confusing me. Right, okay. So this is 14.5,
And
58.
and voltage is parallel is the same.
So these are the same.
Yes.
And there's a voltage here as well, though.
Oh, but 2n is will suffer.
2 what?
2n.
2 N?
M.
2 amp is separate, yeah. It's not the same.
Yes.
So okay, let's make some. Okay, this has some voltage here. We don't know. So Kirchhoff said 14.5 minus IOR
Yes.
4. Oh look, we know here the voltage is 4
Yes.
because we know it's 2 and 2.
Yes.
So if that's 4, then it means here must be 10.5.
Yes.
And these must be the same.
Yes.
Yeah?
Yes.
And we also can calculate
So,
the current, yeah.
yes.
So the current is V over R.
Yes.
That's 10.5 over 58. What's that? 0.18 amps. Great, perfect. So part 1, the lamp will be less bright, yeah. Not dark, the word we use is dim. And part 2, why? And the reason is the current
Is,
fell from 0.25 amps to 0.18 amps. Or
I just write A total equals A1 plus A2 and I draw a little graph.
okay, fine. Okay, fine. Yeah. Oh, and also, not only does the current drop, but doesn't the voltage drop as well? It goes from 12 point. What was the voltage previously?
10.5.
No, it was 14.5.
Yes, and
And the voltage also falls from 10.5, 14.5 to 10.5 volts. Now that's, remember, because P equals IV, if I drops and V drops, then the P
drops.
must also drop as well. Yeah.
FOL,
Falls, yeah.
not FA.
Sorry, no, that is an A. Sorry, Ben. FA, yeah. Okay, next.
Voltage also.
Yeah, continue. So the next one is semiconductor diode. Sketch the circuit to draw the IV characteristic.
Like this.
Perfect. Perfect. Did you draw it too, Ben?
What?
The circuit.
I show you.
Yeah, you drew it. It was okay. Yeah, so I don't need to draw it, do I?
No.
Sketch the graph. Now, some of you had a little trouble with the graph. This is what the graph looks like. There's V in volts. There's I in amps.
Yes.
And it's flat first, and then it increases. And this number here is about 0.8 volts.
IV.
Oh, sorry.
0.7.
Yeah, no, it's yeah. It's 0.7.
Yes. I just looked at it.
I was off by 1, so 0.1. And then on the other side, it's like this.
Your right is 0.8.
Yeah, I'm sorry. He told me I wrote 0.7 in the notes. And we put in some names. What was this part called? Do you remember?
12.
Runaway?
12
45.
voltage.
Yeah, but what was this part called? Breakaway, was it? Runaway?
The same thing. Up and down. Also break.
No, because this one is working right. You want this to happen. Okay, I'll explain. This, what way do we draw it? Like this, isn't it? With a circle.
Yeah.
From back to the.
Like this?
Yeah.
No, just.
No circle?
No, it's not circle. It's
Oh, show me. I can't remember.
Oh,
this
it's
one.
Oh, yeah, the line, sorry. Like this, isn't it?
Yes.
Yeah?
current.
And you need to.
Yeah. This is what you want. You want this. This is its job. Yeah, this is what you want it to do. You want it to do this. From minus infinity. So, it's like, I'll show you. It's like the door. Look here. Look. I'm looking. You want the door to work like this. A little force, okay, a little force won't open. A little more force won't open. But then enough force it starts to open. Okay, so that's like here. A little current, a little voltage, no good. A little more voltage, no good. Enough, 0.7 voltage, off we go. And then you want the opposite not to happen. If I push, doesn't open. If I push more, doesn't open. But in real life, if I push too much, I break it and it will open. So if I go like really too much force, it will open. Okay, so this is what you want. This would be perfect. But you can never do this in real life. So we only say it breaks here. It doesn't break here because we want it to do this. Okay. So when it goes down here, we say this is the it breaks here. Okay. So where's it gone? Here. But I think this had a special name, didn't it? Didn't we call it like runaway? It breaks.
Broke down.
Yeah. Okay, whatever, fine. Right, lastly. Oh yeah, lastly.
So
Yeah.
I use if the electrical circuit's current is too big, the diode will pass.
Correct, yeah, that's it, yeah, that's it. So, Summer has the answer here. If you put the little diode here, and then you put the ammeter here, and here's the current. If I becomes too big, most of the current passes through the diode and not the ammeter. This protects the ammeter from big currents. Okay, so what happens is, we explained in class how this works, but the idea is if this current gets too big, then most of it will move on the top and only a little will move on the bottom. This is the good idea.
We want to know how much the current.
Correct. So if the current is small, then most of it will go in the bottom and a little go on the top. And so the answer will be nearly perfect. Well, because, okay, let's take an example. Let's say this is 0.1 amps. Okay? What will probably happen is 0.099 amps will go this way and 0.001 amps will go here. Is this right? No, because it's nearly right. But it's not perfect. If the current gets very big, like 10 amps, then this will become maybe 9.999 amps, and this will become 0.001 amps. And this is totally wrong. Now, remember when you used the ammeter in the classroom, do you remember you had to pick the setting? 10 amps, 20 amps. The reason for that is to protect it. So, if you set it to 10 amps, that means the current should be less than 10 amps, because if it's more than 10 amps, your answer might be wrong because of what's happening here. Yeah, so for example, maybe this needs to be less than 1 amp. Yeah. But your answer's good.
But I didn't say the last sentence.
No, you don't need to.
Yes, I know.
What did you say?
Last sentence is the ideal diode is broken and the ammeter won't be broken.
Yeah.
Yeah, I need to delete this.
No! What you just said is this, protects.
Okay.
But you can say all those words in just one word, protect. So you can say, what you said, Summer, is that the diode protects the ammeter. So this means if the diode breaks, the ammeter doesn't. You know this word, protects?
Yeah,
It's useful.
So Batman protects his
Exactly. Correct. And if Batman breaks,
So Gotham will be buried.
perhaps. Okay, we can close that? Right, is there more to this? Okay, so what we'll do, we will take a break, and then when we come back, we'll do maths. Now, are you going to get breakfast?
So,
Huh?
so
Are you getting breakfast, Gail?
Porridge.
Good man. Good man. You will get porridge?
Again.
Good. Get it now?
No.
Oh, you had it already?
Yeah.
Oh, good. How much of a break do you want? 20 minutes? 20 minutes? And how many cigarettes? How many cigarettes do you want?
good home.
1 cigarette, 5 minutes? 4 cigarettes? 20 minutes? Okay, 20 minutes. 11:05. Okay, fine. I'm going to make coffee.